Hello everyone, this is Professor Roman. Welcome to the 12th video in my video lecture series, An Introduction to Discrete Mathematics. In this video we're going to discuss Boolean functions in disjunctive normal form. One of the most important practical uses of logic is in the design of what are called logic circuits, which are used in computers. And the idea is that transistors can be made to function as very fast binary switches. And so it's possible to design simple computer circuits that can perform conjunction, disjunction, and negation of their inputs. These are called AND gates, OR gates, and inverters, respectively. So for example, an AND gate can take two inputs, P and Q, which will be described in terms of either a high voltage, denoted by 1 or T for true, or low voltage, denoted by 0 or an F, and output the conjunction. Using combinations of AND gates, OR gates, and inverters, and sometimes other types of gates, circuits can be designed that could, for example, add binary numbers, compare binary numbers, and perform other functions relevant to computer operation. Combinations of these gates and other gates make up what are known as integrated circuits, or sometimes just called chips. Now, the proper study of the design of integrated circuits, of course, belongs to a course in computer logic or computer design. But what we can do here is discuss the connection between logic circuits and compound statements. And that will allow us to construct some simple circuits that perform relatively simple operations. But in order to have a meaningful discussion of the design of simple logic circuits, we have to discuss some related concepts. That's where disjunctive normal form comes in. So we're going to do that in this section, in this video, and in the next one, we'll actually design some circuits. For this chapter, we need some notation. We need to change some of the notation we've been using. I'm going to use the prime symbol for negation. So this would, x prime would be read not x. And this is going to save some hassle with unpleasant sets of parentheses and things, because we don't ever need to parenthesize x prime. Also, I'm going to denote false by 0 and true by 1. And we're going to use this binary alphabet. Compound statements are going to play a key role in our discussion, but in the present context, they are generally referred to as Boolean polynomials. And here is the formal definition. Let x1, x2, x3, and so on be a sequence of statement variables. Any compound statement in these variables, and involving only a finite number of variables, of course, will be called a Boolean polynomial. And so this notation will represent a Boolean polynomial in the variables x1 through xn. When there are 4 or fewer statement variables, I'm probably going to switch to x, y, z, and w. That way I can avoid subscripts. It'll make the polynomials a little bit more readable, I think. And there are two special polynomials. The zero Boolean polynomial of n variables is simply 0 and the one polynomial in n variables is simply denoted by 1. Okay. These will be considered Boolean polynomials, 0 and 1. So here are some examples of Boolean polynomials. Everything here is pretty straightforward, but you do have to remember to put sufficient parentheses so as to avoid any ambiguity. Actually, Boolean polynomials are quite similar to ordinary polynomials that you would have studied in high school algebra, college algebra, or calculus. Ordinary polynomials, though, are often thought of as functions that take on real values. So here's a polynomial of two variables. It's a function from the Cartesian product r cross r into r. This is a polynomial in two variables. Boolean polynomials can also be thought of as functions, but they are functions on the binary alphabet, and they return a binary a bit. So they're functions on 0, 1, and return a 0 or a 1. So for example, this Boolean polynomial is a function from b cross b into b, and here are its values. P of 0, 0 is 0 and 0 prime, or 0 and not 0, and that's 0 and 1. And since this is a conjunction, 0 is false, 1 is true, this is false, 0. And the others work in the same manner. By definition, this Boolean function, which we also could denote by 0 itself, takes the value 0 for all values of the variables. It's a constant function that takes the value 0. This is the constant function that always takes the value 1. So in general, a Boolean polynomial in n variables defines a Boolean function of n variables. Okay. When a Boolean polynomial is thought of as a function, we'll call it a Boolean function, or sometimes it's called a truth function. And we did discuss these briefly some time ago, where the notation was a little different. We talked about truth tables being the same as truth functions, where the variables can take on either t or f, and the function returns either t or an f. Now we're using 1 and 0 for t and f, but otherwise it's only a change in notation. The most convenient way to describe a Boolean function is by writing down its truth table, because that displays all of its possible values. So here's an example. And as I mentioned before, when you design truth tables, when you construct them, it's critically important always to list the variables, their values, in the same order. So the rows should be in the same order every time you construct a truth table, because there's a tendency for people only to look at the last column, and if you change the order of the rows, it will change the values in the last column. It is possible for two different Boolean functions or different Boolean polynomials to have the same truth table, in other words, to have the same truth values. And in fact, that happens precisely when the polynomials are logically equivalent. So we have a theorem: two Boolean functions have the same truth table if and only if they're logically equivalent. Now, given a truth table with 2 to the n rows, we would like to be able to find a Boolean function of n variables whose truth table is that table. So we're working backwards now from the previous example. instead of going from Boolean function to truth table, we want to go from truth table to Boolean function. Okay. And I think the best thing to do is for me to illustrate this with an example. There are many techniques for doing this, but I think this is the simplest one. So let's take a look at this truth table. Okay, it has 8 rows, 2 cubed. So we're looking for a Boolean function of 3 variables whose truth table is this table. And here's what we do. First, we locate each row that ends in a 1. And I've marked those with arrows. And extract those rows into a smaller table just for convenience so we don't accidentally look in the wrong row. For each of these rows, we create a conjunction with 3 variables because there are 3 statement variables here, x, y, and z. And E1 will be either x or x prime. Similarly, E2 will be either y or y prime. E3 will be either z or z prime. And we make those choices in order for the term to be 1, 1, 1. 1 conjoined with 1 conjoined with 1, which is true. We want the term to evaluate to true. So whenever there's a 0, we need to include a prime. So here are the assignments. First row, all 1s, no primes, x and y and z. Second row, we need a prime for y, but not for x or z, and the others are similar. Then we take these conjunctions, there'll be 4 of them because there are 4 rows here, and we take their disjunction. You can see now why it's really important to have a pretty good grasp on the 2 terms, disjunction and conjunction. It takes a while to be comfortable with that, and if you don't tell anybody else, I'll admit that once in a while I screw up. But anyway, each of these in parentheses is a conjunction, and we take the disjunction of those terms. Okay. So we get something rather unpleasant. It's kind of long, and I'm going to leave it for you to do the unpleasant part and check that the truth table of this polynomial is this truth table. Okay. If you're clever, you might be able to reason that out without actually having to construct the table. Now there is one little glitch, in a sense. If the last column of our truth table was all 0s, this wouldn't work because we would have nothing left here. But a table, all of whose values are 0, is the truth table of a contradiction. And that's where this special polynomial comes in. This always evaluates to 0. Okay. So we have a way to construct a Boolean function for any given truth table. Now, this Boolean function, sort of unpleasant as it might be, does have a rather special form. It's the disjunction of conjunctions. Okay. And that has a name. A Boolean function is said to be in disjunctive normal form if it's the disjunction of a finite number of distinct conjunctions of this form. So all the conjunctions have the same number of variables, n variables. And the e's, so e sub I is either x sub I or x sub I prime. These conjunctions have different names depending on who you ask, but sometimes they're called min terms. There are some other names for it. Frankly, I can't remember offhand what they are. You can just call them terms in the disjunctive normal form, but min terms, I think, is a standard terminology. And because of this issue with contradictions, I'm going to say that this function is also considered to be in disjunctive normal form. Not everybody does that, and you don't have to. We're going to stick with it, but if I left this out, then I would have to say any Boolean function that's not a contradiction. Sorry, I meant to say any truth table that's not a contradiction has a disjunctive normal form. There's a polynomial disjunctive normal form with that truth table. So you've got two choices here. You either allow this to be in disjunctive normal form, in which case you can say that any truth table is the truth table of a function in disjunctive normal form, or you can leave this out and say that any truth table that's not a contradiction, all zeros in the last column, has a polynomial in disjunctive normal form with that truth table. So you got the two choices there. Frankly, I'm not sure which is more common, but you need to be aware of those two possibilities. And I think it's a little simpler just to say that the zero polynomial is in disjunctive normal form. And that way, we can say somewhere down here, every truth table is the truth table of a Boolean function in disjunctive normal form. If we reverse the roles of disjunction and conjunction, we get something that's referred to as conjunctive normal form. So a polynomial is in conjunctive normal form if it's the conjunction of a finite number of distinct disjunctions. And those are sometimes called max terms. I noticed a lot of terminology, and not only is it a lot of terminology, but it's not very pleasant terminology. But we're kind of stuck with it because it's standard terminology. Disjunctive normal form is often just written DNF, and this would be CNF. I don't think that solves a problem. You still have to face the terms disjunctive and conjunctive. But we're only going to need disjunctive normal form, so you don't have to worry about conjunctive normal form. Once you get used to this concept, it'll be easy to switch between the two if necessary. So these polynomials are in disjunctive normal form. Polynomial one variable, x. Polynomial of two variables, this is just one min term, x and y. Here is a polynomial of two variables with two min terms, or let's just say two terms, x and y prime, or x and y. So one thing that might help with the terminology is disjunctive normal form is a disjunction. Conjunctive normal form is a conjunction. Disjunctive normal form is a disjunction of what? Well, the only other one, the only other operation, conjunctions. Okay, so maybe that'll help you remember what disjunctive normal form is. It's a disjunction of the only other possibility, and that is conjunctions. This polynomial is not in disjunctive normal form, and I'll let you examine it to see why. So the method of this previous example shows pretty clearly that it's going to work for any truth table. In particular, as long as there's a 1 in the last column, you'll have some rows here, and you'll have something to work with. Again, if it's all zeros, then by our convention, the 0 Boolean function takes care of that case. Okay. So we can say then that every truth table is the truth table of a Boolean function in disjunctive normal form. Okay. You see, it's the truth table that we're going to use to get the behavior we want from a particular circuit. If we want the circuit to compare inputs, true and false, depending on whether the inputs are the same or not, or to add binary numbers, we're going to construct a truth table that will do that. But then we need a Boolean polynomial in order to construct the circuit. So that's the direction we have to go in, and that's why this is so critically important. Okay. So given any Boolean function, we have a method for finding we have a method for finding another Boolean function that's in disjunctive normal form, that's logically equivalent to the polynomial or function we started with. What do? We take P, we find its truth table, and then from that we can construct Q. So here is a polynomial. It's not in disjunctive normal form. But we compute its truth table, then use the method we did in the last example, and we get another Boolean function that is in disjunctive normal form. Now, so these two polynomials are logically equivalent. They always take on the same truth value because they have the same truth table. Of course, your first reaction is, well, why make this more complicated? P is a much simpler polynomial than Q, and that's very true, but we need Q to construct the circuit that has this behavior, the behavior described either by the polynomials or by the truth table. Okay. All right, so there's some trickiness here. If you're not entirely comfortable with it, I would suggest that you re-watch the video, because if you're interested in logic circuits, you're going to need to have a fairly good grasp on this material. Okay, thank you for watching the video, and hang in there, and I hope to see you in the next video.